A coil having an area of 2 meters square is placed in a magnetic field which changes from 2 Weber per meter square to 5 Weber per meter square in 3 seconds. The EMF induced in the coil will be 4 volts, 3 volts, 2 volts or 1 volt. Okay, so here the EMF is induced in the coil because of the change in the magnetic field, and so that will be E equals to minus d phi upon dt. Okay, so this change in the magnetic field depends upon this phi will be depend upon the magnetic induction, magnetic field multiplied by the area. So that is nothing but a phi, that is the change, that is firstly we have the change from 2 to 5, so that will be b2 minus b1 upon t. Now we put the values. Area is given 2 meter per second, 2 meter square, multiplied by this is 5 minus 2 upon this time is t, that is 3 seconds. So that will be 5 minus 2 is 3, 3 2 is 6, and that is 6 upon 3, that will be again 2. So that is 2 volts of EMF is induced. So that is C is the correct option 2. Next, two rails of railway track separated by 1 meter and insulated from each other are connected to a millivolt meter. What is the reading of the millivolt meter when a train passes at a speed of 180 kilometers per hour along the track? The vertical component of the Earth's magnetic field is 0.2 into 10 raised to minus 4 Weber per meter square. So the options are 1 volt, 100 millivolts, 1 millivolt or 10 millivolts. Okay, so basically what we are given is we are given two rails separated by a distance of length, that is 1 meter, and next we have a train which is traveling at a speed, that is velocity is 180 kilometers per hour. So we can convert to meters per hour, that is 180 multiplied by 5 upon 80. Okay, next is we are having the Earth's vertical component magnetic field in vertical component, that is 0.2 into 10 raised to minus 4. Okay, so with the formula which we have in order to find the millivolt meter, that is the EMF which is induced, that is given by BLV, where B is 0.2 into 10 raised to minus 4 into the length will be 1 into V, that is 180 into 5 upon 18. And solving this we get a value of 1 millivolt. Okay, so here C is the correct option. A coil of effective area 2 meters square is placed at right angle to a uniform magnetic field of induction B. When the field reduces to 10% of its original value in 0.6 seconds, an EMF of 0.24 volt is induced in it. The magnetic induction is 0.02 Weber per meter square, 0.04 Weber per meter square, 0.08 Weber per meter square, or 0.1 Weber per meter square. So here we have an effective area given. So that is A, which is equals to 2 meters square, placed at a right angle in a uniform magnetic field of induction B. And when the field reduces to 10% of its original value, that is the change in the field dB is going to be 1 minus 0.1, that is 1 upon 10. So that is 10 minus 10% of its original value, that is given to be again 0.9 times of B. Okay, so it is an EMF is induced. The time given is 0.6 seconds and EMF induced is 0.24 volts. Okay, so we have EMF which is equals to d phi upon dt, which depends on the magnetic induction upon and multiplied by the area upon dt. So if we keep the area, we need to find the dB, we need to find this the value for B. So we'll keep the A out here, so dB upon dt. So changing it will be, it becomes equals to dB becomes equals to E dt upon A. So this will be our formula. So E has a value, again dB has a value of 0.9 B, which is equals to E has a value of 0.24 multiplied by dt has a value of 0.6. Okay, multiplied by divided by A, area is 2, so that gives you value 0.072. so B will be again equals to 0.08, we can say, we'll round it off, significant figure, so the Weber per meter square. So C is the correct option. What is the change in the magnetic flux produced in a coil of in 25 seconds if the induced EMF in the coil is 2 millivolt? 5 into 10 raised to minus 2 Weber, 12 into 10 raised to minus 2 Weber, 7.5 into 10 raised to minus 2 Weber, or 15 into 10 raised to minus 2 Weber. Okay, so we need to find the change in the magnetic flux, that is d phi, which is equals to E dt. Okay, next it is E, which is given as 2 millivolts, that is 2 into 10 raised to minus 3 into the time that is given as 25. So that will be, multiplying all this, we get 5 into 10 raised to minus 2 Weber. Okay, so this is the change in the magnetic flux. So that is option A is the correct option. A meter gauge train is running towards north with a speed of 20 meter per second. If its vertical component of the Earth's magnetic induction is 3 into 10 raised to minus 4 Weber per meter square, then the EMF induced at the ends of the axle is 3 millivolt, 6 millivolt, 12 millivolts, or 18 millivolt. We need to again find the EMF induced, okay, where which is being given by E is equals to BLV, where your B is the vertical components of the Earth's magnetic field, that is 3 into 10 raised to minus 4 Weber per meter square. Your length here will be equals to 1 meters, which is given, which is for, we consider as for a gauge, for a meter train, it is the length is obviously 1 meter. Next we have a speed velocity 20 meter per second. So substitute all the values, that is 3 into 10 raised to minus 4 multiplied by 1 multiplied by 20 gives you 6 millivolts of EMF induced. That is B is the correct option. The magnetic flux in a closed circuit of resistance 20 ohms varies with time t, and according to the equation phi equals to 8t square minus 6t plus 5, what is the magnitude of the induced at what is the magnitude of induced EMF at the time t equals to 1 second? Okay, and the options given are 0.1 amperes, 0.25 amperes, 0.5 amps, 0.75 amps, or 0.1 amps. So we need to find the current out here, and that will be given by this formula E equals to d phi by dt, where this is the change in the flux, which is given as phi, that is 8t square minus 6t plus 5. So we will differentiate this with respect to time t, so we get 16t minus 6. Okay, so that will be at time t equals to 1, so that will be 16 minus 6, that gives you 10 volts, okay, of E. Again we need to find the current I, which is equals to E upon R. So E we found about 10 and R is given to be 20 ohms, so 10 upon 20, that gives you 0.5 amps of current. So B is the correct option. Dimensional formula for magnetic flux is, so we need to get the formula for the magnetic flux. Phi, we know that it is multiplied, the magnetic induction multiplied by the area, but for that first we need to find the magnetic field, that is B is equals to, we know it is we know that the force is equals to BIL. Okay, so we'll get the B through this, that is F IL upon F, sorry, so that will be B equals to F upon IL, sorry, F upon IL. So we can get this dimensions of force, that is m1 l1 t raised to minus 2 upon the current, that is upon the current multiplied by the length. So the length will be 1 and the current A becomes again 1. Okay, so in all we get this as m1 L becomes 0, t raised to minus 2, a raised to minus 1. Okay, next we have the, we found B, we will substitute the value of B over here and multiplied by the area. So phi becomes equals to m1 L0 t raised to minus 2, a raised to minus 1 multiplied by the area, that is length square. Okay, length 2 to the power 2, so that becomes m1 L2 t raised to minus 2, a raised to minus 1. Okay, so this is the option number m1 L2 t raised to minus 2, a raised to minus 1. D is the correct option. Okay, so a magnetic field of 2 into 10 raised to minus 2 Weber per meter square acts at a right angle to a coil of area 100 centimeter square with 50 turns. The average EMF induced in the coil is 0.1 volts. When it is removed from the field in t seconds, what is the value of t? 1 second, 0.5 seconds, 0.1 second, or 0.01 second. So we have given the value for B, that is 2 into 10 raised to minus 2 Weber per meter square. We have A, that is 100 centimeter square, that will be 100 into 10 raised to minus 4 meter square. Next is N, that is number of turns, that are 50 turns are given. E, that is the induced EMF, that is 0.1 volt, and the time t which we need to find. So for that the EMF induced E is equals to NBA upon time t, so where t becomes equals to NBA upon E. So we substitute all the values, 50 into 2 into 10 raised to minus 10 multiplied by this becomes 10 raised to minus 2 upon 1, the E, that is 0.1 volt, so that will be 10 raised to minus 1. So that we again everything here goes out, it gives us the value 10 raised to minus 1, that is 0.1 seconds. Okay, So the correct option is C, 0.1 second. A magnetic flux passing perpendicular to the plane of a coil is given by psi equals to 60 square plus 40 plus 3, where phi is in milliweber, t is in seconds, and what is the EMF induced in the coil at t equals to 1 second? 4 millivolt, 8 millivolt, 12 millivolt, or 16 millivolts. So here the magnetic flux phi is given to be 6t square plus 4t plus E, and we know that whenever the EMF is induced, this flux changes with respect to, the flux has to change with respect to time. So if we differentiate with this respect to time, we get 12t plus 4. Okay, and if there we have time t equals to 1 second, so this d phi by dt again becomes equals to 12 ones are 12 plus 4, that will be 16 millivolts of EMF is induced. So your correct option is D, that is 16 millivolts. Aeroplane in which the distance between the tips of the wings is 50 meters is flying horizontally with the speed of 360 kilometers per hour over a place where the vertical component of the Earth's magnetic field is 2 into 10 raised to minus 4 Tesla. The potential difference between the tips of the wings will be 0.1 volt, 0.5 volt, 0.0 or 0.2 volts or 1.0 volts. So here what we are given is, here there is a length given that is of 50 meters, and there is a velocity that is 360 kilometers per hour. So that will be again 360 multiplied by 5 upon 18. Okay, and the vertical components of the Earth's magnetic field, that is 2 into 10 raised to minus 4 Tesla. Okay, so we need to find the EMF induced, that will be given by BLV, where B is 2 into 10 raised to minus 4 into the length, that is 50, multiplied by the velocity, that is 360 into 10 raised to 5 upon 18. So on solving all this, we get a value of 1 volt of EMF is induced. So D is the correct option. A coil of 0.05 meter square and 500 tons is placed in a magnetic field of strength 4 into 10 raised to minus 5 Tesla. If it is rotated through 90 degree in 0.1 seconds, then the magnitude of EMF induced in the coil will be 10 millivolts, 20 millivolts, 5 millivolts, or 15 millivolts. Okay, so here we have been given the area, that is 0.05 meter square, and the number of tons is 500 tons, and it is placed in the magnetic field of strength B, that is 4 into 10 raised to minus 5 Tesla. If the coil is rotated to an angle of 90 degree, then it will become in 1 second. So T becomes equals to 0.1, we can take in 0.1 seconds. So again we are having the E, which is equals to the EMF induced depends on the change in the flux upon time, where change in the flux is equals to NAB upon time T. Okay, so N is again 500 multiplied by 0.05 multiplied by B, 4 into 10 raised to minus 5 upon the time T, that is 0.1. So all this comes out to be a value of 10 raised to minus 2 volts, that gives you 10 millivolt. Okay, so the EMF E induced is 10 millivolt, so A is the correct option. A metal conductor of length 1 meter rotates vertically about one of its end at an angular velocity of 5 radians, okay, per second. If the horizontal components of the Earth's magnetic field is 0.2 into 10 raised to minus 4 Tesla, then the EMF developed between the two ends of the conductor is 50 microvolts, 5 microvolts, 50 millivolts, or 5 millivolts. So let's write down what all things are given. We have a metal conductor of length L, that is of 1 meter. It is rotating vertically, and it's one end of it, and it has an angular velocity omega of about 5 radians per second. And then if the horizontal components of the Earth magnetic field BH is equals to 0.2 into 10 raised to minus 4 Tesla, then the EMF which is developed E will be equals to, so for that the induced EMF, we have a formula half B omega L square. Okay, where half multiplied by the B, that is 0.2 into 10 raised to minus 4 multiplied by the length, that is 5 into 5 into the length, that is 1 meter square. Okay, omega is 5 radians and length is 1 square. So on solving this, we get a value of 10 raised to minus 4 upon 2, that will be, we can write it as 100 into 10 raised to minus 6 upon 2, so that will be again 50 into 10 raised to minus 6 volts, so that will be 50 microvolts. Okay, so the EMF induced is 50 microvolts, so A is the correct option. A coil of metal wire is kept stationary in a non-uniform magnetic field. An EMF and the current are both induced in the coil. A current but no EMF is induced in the coil, or an EMF but no current is induced in the coil. Neither EMF nor a current is induced in the coil. So if the coil is kept inside if a coil of metal wire is kept inside the stationary inside a magnetic field, and the coil is stationary, that is, it is not moving, that means that the flux is not changing, hence an EMI will not be induced. So neither an EMF is induced nor a current will be induced inside the coil, because for that the required thing is the magnetic flux associated with the coil should change with respect to the time. As a result, if the coil is kept stationary and that in a non-uniform magnetic field, there is no change in the flux, so that neither no EMF or the current will be induced in the coil. So D is the correct option. The two identical circular loops A and B of copper wire are lying on a table without touching each other. The loop is A is carrying a current which increases with time. What is the response in the loop B? It rotates about its center of mass with center of mass fixed. It is repelled by the loop A. It is attracted by the loop A, and it remains stationary. So basically we have a loop A and a loop B, and the current in the loop A is increasing, as a result of which magnetic flux in the B will start increasing. Okay, and the current will be induced inside B also as well. So as per Lenz's law, this B will then start repelling this A, and it is the option number B. It is repelled by the A. There is no center. It does not rotate, or nor it is attracted, or it does not remain stationary. But because of the induced EMF inside B, this B will repel the A, loop A. A telegraph wire of length 2500 meter is kept in a east-west direction at a height of 10 meters from the ground. If it falls freely on the ground, then the current induced inside the coil inside the wire is given that the resistance of the wire is 25 root 2 ohms, G is equals to 10 meter per second, and BH is equals to 2 into 10 raised to minus 5 Tesla. The options we have are 6.1 amps, 0.01 amps, 0.02 amps, or 0.2 amps. Okay, so here what we have given is a length, that is a length of about 2500 meter wire length, and it is kept in east-west direction at a height of about h 10 meters from the ground, and it falls freely on the ground. Then we have G, that is 10 meters per second square acceleration due to gravity. Then we have the resistance R, that is 25 root 2, and we have this magnetic induction at the horizontal component of magnetic field of Earth's magnetic field, that is 2 into 10 raised to minus 5 Tesla. Okay, so we need to find the EMF induced, that is basically the BHL into V, where here V will be nothing but V square, that is we have the formula V square is equals to 2GH. So V equals to under root of 2GH, that will substitute over here. So we get E equals to BH into L under root of 2GH. Okay, so now here what we have is E, which we get is B, that is how much, 2 into 10 raised to minus 5 multiplied by the length, that is 2500 meters, multiplied by the under root of 2 into 9 G, that is how much, G is 10 meter per second square, and the height, that is 10. Okay, so on solving that, we get the E to be 50 of root 2 into 10 raised to minus 2 volts. But we need the current induced in the coil, that is the I. So I is equals to E upon R. So that E is 50 into root 2, that we can have the value for root 2, that is 1.414 into 10 raised to minus 2 upon the resistance which is given is R is given to be 25 into again 1.414 we can have, so that will be 0.02 amperes of current is induced. So C is the correct option. Electron moves along the line AB, which lies in the same plane as the circular loop of the copper wire as shown in the figure. What will be the direction of the current induced if in any loop? So if we have an electron, if we have a conductor and if you have a charge or charge inside a conductor which is moving towards this from left to the right, it will be same like an electron which is moving with its magnetic field outwards. Okay, so due to the electron is moving from left to the right, and EMF will be induced due to its change in the magnetic flux will change, and as a result an EMF will be induced inside this coil. But that will be as soon as the electron will move from left to right, it will go on increasing inside this conductor. But as soon as the electron leaves the place, and thus this induced EMF will also change. So the current what will change the direction as the electron will pass by. So option number will be A. The coefficient of mutual inductance of two coil is 10 millihenry. If the current flowing is one coil is 4 amperes, then the induced EMF in the second coil will be A 40 millivolts, 20 millivolts, 0 or 10 millivolts. Okay, so for a steady current, okay, the current flowing in one coil is 4 amperes, and then the induced EMF in the second coil will be, the coefficient of mutual inductions of the two coils is 10 millihenry. So what we have is the change in the current for a steady current, the change in the current with respect to the time will be 0. Okay, so whatever the EMF will be induced will be given by the mutual inductance multiplied by the change in the current with respect to the time t. So if this factor is 0, then the induced EMF will be 0. So the correct option is C. A coil has an inductance of 1 Henry if a current changing at a rate of 3 amperes per second induces 1 volt in it, 3 volt in it, 3 volt in a neighboring coil, or 1 upon 3 volt in it. Okay, so we have given an inductance L of 1 Henry, and the current is changing at the rate of 3 amperes per second. So the induced EMF will be the inductance upon the change in the current with respect to the time, that is 1 multiplied by the change in the current per second is 3. So that is 3 volts of current is changing. So the correct option is B, 3 volts in it. If a current of 3 amperes flowing in the primary coil is reduced to 0 in 0.01 seconds, the EMF induced in the secondary coil is 750 volts. What is the mutual inductance between the two coils? 1.5 Henry, 2 Henrys, or 2.5 Henrys, or 3 Henrys. Okay, so we have a current I which is of 3 amperes which is flowing through a primary coil. So that current is called the primary coil current, and it reduces to primary coil is reduced to 0 and in 0.1 seconds. So the change in the time dt will be 0.01 seconds, and the EMF induced in the secondary coil ES is 750 volts. So we need to find the mutual inductance M. Okay, so we have the formula ES is equals to M, the change in the current in the primary upon with respect to the time t. So here we already have ES, that is 750. So M multiplied by the change in the current is 3 to 0. 3 minus 0 becomes 3. So that is 0. Time will be 0.01. So the value for M comes out to be 2.5 Henry. So C, 2.5 Henry is the correct option. A long solenoid has 500 turns. When a current of 2 ampere is passed through it, the resulting magnetic flux linked with each turn of the solenoid is 4 into 10 raised to minus 3 Webers. What is the self-inductance of the solenoid? 2 Henry, 1.5 Henry, 1 Henry, or 0.5 Henry? So here we are going to find the self-inductance L equals to. So but also the total magnetic flux with the link with the solenoid will be given by the number of turns of the coil multiplied by the magnetic flux linked with each turn. Okay, so the total magnetic flux phi will be 500 multiplied by the each turn is 4 into 10 raised to minus 3. Okay, so that will be again 2 Webers. Okay, got this? So we are now going to find the value for L. So L equals to psi upon I. So that is 2 Webers upon the current, that is given as 2 amperes. Okay, so a current of 2 amperes goes from there. So we have a inductance of 1 Henry, self inductance of 1 Henry. C. This dimensional formula for the coefficient of self inductance. Self inductance L is equals to dt upon di. So with this E we have the formula work done upon charge, and this is dt upon di. So dt upon di is over here, that is dt having t dimensions and I having one dimension a. Work done, we have the dimension formula for that, L2 m1 t raised to minus 2, and the charge, that is current into time, that is a into t. Okay, so we cancel out the remaining things and we are left with L2 m1 t raised to minus 2, okay, and this a again becomes a square a raised to 2, that becomes goes up and it becomes a raised to minus 2, that is for L. So we have the option L2, t raised to minus 2, a raised to minus 2, and M1. So C is the correct option. An idle coil of 10 Henry is connected in a series with a resistance of 5 ohms and a battery of 5 volts. 2 seconds after the connection is made, the current flowing in amperes in the circuit will be e raised to minus 1, 1 minus C, or 1 minus e raised to minus 1. Okay. So, an idle coil of 10 Henry is connected in series with the resistance. So, uh, this is an LR circuit. Okay, so there is a coil, there is an inductance L, there is a resistance R. So for an LR circuit, the growth in the current is given by this formula: I equals to I0 1 minus e raised to minus RT upon L. Okay, so that I naught is nothing but the peak value for the current that will be given by E naught upon R into 1 minus E minus RT upon L. So we can place the values for this, that is E naught is given to be the peak value, is given to be the current flowing in amperes in the circuit will be, we need to find the current I. So a 5 volt battery is connected, so 5 upon the resistance is 5 ohms into 1 minus E, again resistance is 5 multiplied by the time of 2 seconds upon the length upon the inductance of 10 Henry. Okay, so all solving this, we get the I value is equals to 1 minus E raised to minus 1. So D is the correct option. If n is the number of the turns in the circular coil, then the value of the self-inductance varies as n raised to 0, n raised to minus 1, n raised to 2, or n raised to 1. So we have given the number of turns and we need to find the self-inductance which is varying with respect to the number of turns, that is n varies. So the L inductance, for the self-inductance L, we have, it is the way the formula is n of phi is equals to L multiplied by this I. Okay, the number of turns multiplied by the flux is equals to the self inductance multiplied by the current. So for that, the self inductance value is n phi upon I. Okay, again this phi is nothing but B into A, that is the magnetic field induction multiplied by the area. But the B, which is there is it's a circular coil, so the B at the center of the coil will be given as mu naught upon 4 pi into 2 pi Ni upon R. Okay, so let's place all this together. We have L equals to n phi upon I, which is equals to n phi becomes B into A upon I. So n B that is will be n into A upon I, and that B value again becomes this entire thing, mu naught upon 4 pi Ni upon R. So this is n, this is n, so it total becomes n square, and which we are finding the L. So L is directly proportional to n square. So that is the relation of the self inductance with respect to the number of turns in a circular coil. The time constant of an inductance coil is 2 milliseconds. When a 120 ohms resistance is joined in the series with the coil, the time constant becomes 0.5 milliseconds. What are the values of the resistance in the and the inductance? 20 ohms 50 millihenry, 40 ohms 60 millihenry, 40 ohms 80 millihenry, or 80 ohms 80 millihenry. So here there are two conditions which are given. Okay, according to the first condition, there is a time constant T, which has of an inductance of coil is 2 milliseconds, and when a 120 ohm resistance is joined to the in series with the coil, the time constant becomes 0.5 seconds. So we have this time constant which is related to this inductance and resistance as T tau is equals to L upon R, that is given to be 2 milliseconds, that is 2 into 10 raised to minus 3 seconds. The second case is when this resistance is joined in the series with the coil, so that is L upon this is joined in the series, resistance is joined with this in series, so that is about a resistance of 120 ohms is joined in the series. Okay, so that time the time constant becomes 0.5 into 10 raised to minus 3 seconds. Okay, so we have got the two equations. Now we'll divide those two equations. Let's divide the second upon by first. So what we get is R plus 120 upon this R, the LL gets cancelled, is equals to 0.5 upon 2, so that will be nothing but 4. Okay, into 10 raised to 3, 10 raised to 3. So that is next what we have is here r plus 20. So 120 equals to 4 times r. So r becomes equals to 40 ohms. We can solve this. R becomes 3 ohm. This r goes there, that is 4r minus r becomes 3r. So that is the answer is 40 ohms. Okay, and we have the tau which is equals to L upon r. So L we just found the r, that is about L upon R. So we just found the R, that is about 40 upon L, which is equals to 2 into 10 raised to minus 3. So L becomes equals to 80 into 10 raised to minus 3, that is equals to 80 millihenry. Okay, so your resistance you got is 40 and the inductance you got is 80. So 40, 80 is C is the correct option. The primary and the secondary voltage of an ideal step-down transformer is 200 volts and 25 volts respectively. The secondary is connected to a device which draws a current of 2 amperes. What is the current in the primary? 100 milliamperes, 150 milliamperes, 200 milliamperes or 250 milliamperes? Okay. So this is a step-down transformer which is having a primary and secondary voltage of 225 volts, and the secondary is connected to a device which draws a current of 2 amperes. What is the current in the primary? So we have the current to the voltage ratio in a transformer, that is IP upon IS is equals to Vs upon Vp. Okay, so here IP is given, Is is the current to the secondary, that is 2. Okay, and Vs is given to be voltage to the secondary is 200, voltage to the secondary is 25, and voltage to the primary is 200. Okay, so your IP becomes equals to 1 upon 4, that is amps, that is equals to nothing but 250 milliamps. So D is the correct option. Primary and the secondary coils of a transformer are 50 and 1000 turns respectively. If the magnetic flux linked with the primary coil is given by phi equals to phi naught plus phi t, where phi is in Webers, phi naught is a constant and t is in seconds, then output voltage across the secondary coil will be 50 volts, 75 volts, 100 volts or 220 volts. Okay, so what we have given is we have given a relation, that is 5 is equals to phi naught plus 5t, and the voltage across the primary, first the primary and the secondary coil, the voltage across the primary will be depending on the flux. Okay, so that is nothing but we will differentiate with this with respect to time, so we get it as 5 volt. And next we have the equation for the ideal transformer equation, that is Vs upon Vp is equals to Ns upon Np. Okay, so we have the we need to find the voltage across the secondary. So Vs is equals to Vp, voltage across the primary is 5 multiplied by Ns, that is the secondary turns coil, that is the secondary turn we are having 1000 volts, upon the primary we are having 50 volts, 50 turns. Okay, so that becomes 5, so that becomes 10, sorry, it is 1000 volts and it is 50 volts, so that becomes 100 volts through the secondary coil. Okay, so C is the correct option. The instantaneous current in an AC circuit is given by I equals to 2 sin omega t plus 5 amperes. The RMS value of the current is 2 amperes root 2, 2 root 2 amperes root 2 amperes or 1 upon root 2 amperes. Okay, so here what we have is we have given the instantaneous current, and that is nothing but I, which is equals to 2 sine omega t plus 5 plus theta. Okay, so that will be the I RMS value. We will compare it with the ideal equation I0 sine omega t. Okay, so your I0 becomes equals to 2. Okay, and we have to find the I RMS value. So I RMS is equals to I naught upon root 2, where I naught is 2 root 2. So I RMS becomes 2. So I RMS will become again root 2 amperes. Okay, so that will become root 2 amperes. So that is root 2, because we can take this 2 as equals to root 2 multiplied by root 2. So root 2 gets cancelled. What you are left with is root 2 amperes. So an alternating EMF is given by E equals to 10 cos omega t. If the frequency of 50 Hz, then at a frequency of 50 Hz, then at the time t equals to 1 upon 600 seconds, the instantaneous value of EMF is 5 volts, 1 volts, 10 volts, or 5 root 2 volts. So here we have E equals to 10 cos omega t. So we compare it with this, that is equal, it will be equals to 10 cos omega, that will be nothing but 2 pi n t. Okay, and that is 10 cos 2 pi multiplied by this n, that is the frequency, that is given as that there is a time, that is 1 upon 600 multiplied by n, frequency that is given to be 50 hertz. So your E value comes out to be 10 cos pi by 6, which is nothing but 10 cos pi by 6 gives you root 3 upon 2. So that becomes 2 1 2 5, that becomes 5 root 3 volts of EMF is induced. So 5 root 3 volts of EMF is there. So the correct option is, what we have here is D. So that is 5 root 3. In an AC circuit, the current is given by I equals to 6 sine 200 pi t plus pi 6 amps. The initial value of the current is 1 amp, 2 amp, 3 amps, or 4 amps. Okay, so we have I, which is equals to 6 of sine 6 sine 200 pi t plus pi by 6. Okay, so this is the value at the initial value of the current. At the initial means at time t equals to 0. So at time when time t equals to 0, we have it is equals to 6 sine pi by 6 only. Okay, so this becomes 0. So that is nothing but 6 into sine pi by 6 is half, so that becomes 3 amps. Okay, so C is the correct option. From the two EMF equations, E1 equals to E0 sin 100 pi t and E2 equals to E0 sin 100 pi t plus pi by 3, we find that E1 leads E2 by 60 degree, E2 lags behind by 60 degree. E2 achieves its maximum value of 1 upon 300 seconds before E1, and E1 achieves its maximum value 1 upon 300 seconds before E2. So let's write down the equations first. E1 equals to E0 sin 100 pi t and E2 equals to E0 sin 100 pi t plus pi by 3. So basically, as you can see here, the omega t is equals to, both of them we have the same, that is 100 pi t. So that means the frequency out here is coming out to be 50 hertz. That is for this time t equals to 1 upon 50 seconds. Okay, so the frequency is 50 hertz for time t equals to 50 seconds. But if we need a phase difference of 2 pi, then the time required is 1 upon 50 seconds. But here the phase difference is pi by 3. So for a pi by 3 phase difference, the time required is pi by 3 multiplied by 1 upon 50. So that gives you 1 upon 300 seconds. Okay, that means this E2 is leading, okay, and it achieves its maximum the value of 1 upon 3600 seconds before E1. So C is the correct option. Okay, the household supply voltage as measured by an AC voltmeter is 220 volts. If the frequency of AC supply is 50 Hz, then the equation of the line voltage will be V equals to 220 sine 100 pi t, V equals to 110 sine 50 pi t, V equals to 410 sine 100 pi t, or V equals to 311 sine 100 pi t. Okay, so for that first we need to the V naught we need to find out, and for that we need the angular frequency, that is the frequency of the AC supply. So omega we have it to be 2f into n, that is 2 pi into n, that is the frequency. So 2 pi multiplied by the frequency, that is given to be 50 hertz, so that gives you 100 pi of omega. Next we have know the value for VRMS, root mean square velocity, is given by the peak value upon root 2. So V naught will be nothing but root 2 multiplied by the VRMS, which is given to be 220 volts. So root 2 multiplied by 220 volts, that will be root 2 ka value is 1.414 multiplied by 220. So this will give you the value 311 volts, that is VRMS. Okay, now we put all these things together. We know the formula, V equals to V naught sine omega t. Sorry, this is V naught. Okay, V equals to V naught sine omega t. So V naught is 311, sine omega is 100 pi t. So that is D option, 311 sine 100 pi t. Current wave in an electric circuit consists of two components. It consists of two components. Number one is a 10 DC component, and number two is a 50 hertz component AC, having a sinusoidal waveform, and which has the peak value of 10 amperes. At the time t equals to 0, the AC component has 0 value, and at di upon dt it is positive, and the average value of the resultant current over the complete cycle is, so we need to find the average value of the resultant voltage over the complete cycle. So here there are two components, that is there is a DC component and there is a 50 hertz AC component. So for an AC component, what we have is the average value for an AC component over a complete cycle, it becomes 0. Okay, so all we get is a DC component, that is of about 10 volts, 10 amps of current. So the final value will be option number B, 10 amps of current. A pointer of deadbeat galvanometer gives a steady reflection because its pointer is very light. Its frame is made up of ebonite. Eddy currents are produced inside the conducting frame over which the coil is wound, or its magnet is very strong. Basically, in a deadbeat galvanometer, the coil is wound on a metallic frame. Okay, and the eddy currents are produced inside this frame, which produces electromagnetic damping. Hence, whenever the current is passed through it, the pointer comes to rest immediately without producing any oscillations in the coil. And so, whenever there is a inside the deflection, current passing through the deadbeat in a deadbeat galvanometer, the pointer produces eddy currents. Okay, so eddy currents are produced in the conducting frame over the coil is wound. Self-inductance L of a solenoid of length L and area of cross-section A with a fixed number of turns N increases as L and A increases, L decreases and A increases, L increases and A decreases, both L and A decreases. Okay, so the self-inductance of a solenoid L is given by this equation mu naught into mu R. Okay, where it will be multiplied by this N square number of turns multiplied by the area multiplied by the length, where the small n will be capital N upon L. Okay, number of turns upon the length. So if we have this L equals to mu naught mu R, if we substitute this value, we have N square upon L square into A multiplied by this length. So this length will go. So what we have left with mu naught mu R into N square A upon this length, which is the inductance. So here what will happen is L will decrease and A will increase. So those are inversely proportional. L is inversely proportional and A is directly proportional. So the correct option is B. L decreases and A increases. If this L increases, then this A will increase with it, but this L will decrease downwards.